Our next presenter is Dr. Thomas Reiner. He is head of operation and development of Hekla Borey Dent. After studying at the Martin Luther University Halle-Wittenberg, he specialized in the field of laser and glass material science. His specialty is laser-induced formation and modification of nanoparticles in glass materials. From 2000 up to 2017, he was the managing director of Borey Dent. And since 2017, Borey Dent is part of the Hekla Group. He is heading the operation and research department. Today, he will talk about laser glass processing next generation. We're looking forward. The stage is yours, Thomas.
Thank you. Thank you for the introduction. Ladies and gentlemen, good morning. I want to try to make a lecture in the mission and vision of the GPD. So I have here a case study of a problem that's facing us in the laser glass processing. And I want to introduce you to follow our way to solve this problem. I will divide my lecture in such parts. First of all, I will introduce a little bit the state of the art for laser glass processing and to show you what's the limits and in the next step to find the bottleneck and to solve the limit. This I want to show you on an example on a step IGU production and then to summarize my lecture. Here you can see typical equipment. Since more than 20 years, the laser is a tool in our world of glass processing. It starts with laser marking via laser transfer printing for the purpose of track and trace. And since more than 15 years, we have such huge machines, vertical ones, where we can do some patterning on coated glass and even on uncoated glass for different applications. And this is a typical example of such a machine. It's an XY portal inside with linear drives, and we have minimum, of course, one laser and maximum 3 laser in it. And to show you how it works, I have a small movie. And this machine is is like a CNC machine for the glass industry. We have there different tools inside and can use this. Not in kind of different drilling elements. We have different laser tools in terms of laser recipes as well as laser sources. And so we are able to do different things with one machine. It's a multifunctional machine. And in most cases we modify coding or even we remove the coding like we can see here and then produce for different applications like heated glass, like the glass you're facing with the problem in modern buildings with the less communication for the smartphone with the damping effect of the low E coding. All the things we can solve with laser as a tool. And even if you can see here, we can remove areas from the glass or decorate glass. All the things are possible with such a laser as a tool, and since more than 15 years we have it in our industry. The question is where we have it in our industry. Here you can see it, a typical layout of a glass processing company. It starts on the right-hand side with the cutting of the glass, of course, then edge seaming, we have the laminating, we have the toughening, and at the final end, it's an IGU production, isolated glass units, we have the IGU production. And if customers are interested in laser processing, they ask for, okay, where I can stand the machine, and in the most cases, the space in the shop floor determines the position of the machine. And so we have it then on different classes, different places. Sometimes we think about it, okay, it would be fine to have the machine in front of the IGU line. Yeah, and if we want to do this, then we have to think about, okay, match the processes to each other. And if we look to an IGU process, then we see, okay, it's a really, really fast process. We have customers, they produce IGUs in 15 up to 30 seconds, so we are in the terms of seconds per piece. Yeah? If you look to the laser processing, unfortunately, we are on the terms of minutes per piece or minutes per square meter. And this is why we can't do this in the front of the IGU line, positioning the laser process. Yeah. And the question is why it is there. And if you have a little bit of a closer view to the laser process here, you see an example of structuring low-E coding. On the right-hand side, you see the laser forms some patterns, and these patterns in a low-E coding, remove the low-E coding to have then a better access by smartphone inside concrete steel buildings with modern high-performance windows. And you see the laser do this circle by circle, yeah, each after each other, and this leads to this process time pieces per minute. Yeah. And why it is the case? If you look to a typical laser tool, it consists of a laser source, a scanning device, and a focus lens that brings the right energy to the workpiece to modify or remove coating. Then, if you look to the laser source, fortunately, there's a lot of laser sources in the market available, and you can nearly freely adjust the speed. It's mostly a pulsed laser, and adapt it to the application requirements. Yeah. So the laser is not the problem itself. If you look to the next step, then we see the laser has to be moved over the coded class. And here we have an optical scanning device, consists of two mirrors, rotating mirrors. And if you look a little bit closer, then we see, okay, there's of course a maximum speed, but this maximum speed is our limit. This is the reason why we can't speed up the process. And the question is how we can solve this. And to give you a little bit more impression, what does it mean if you do a coating removal, I will go a little bit more in detail for the application or production of step units. What is a step unit? A step isolating unit is a normal IGU, but one pane is a little bit longer, and this is the coated pane. And in this area here, the coating has to be removed because this will be printed with ceramic color and then mounted in the facade. So we have to remove a really broad stripe of 50 up to 100 millimeter by laser, and this takes time. So even if we do this with maximum speed, you see a picture of the removal displays. We remove the coating. We have only one possibility in this case. If you run the scanning device with the high speed, we can reduce the resolution of the removal. What we do is we have lines, we have overlapping lines, and we can remove the removal, the resolution. In this case here for the 40 micron resolution with the highest resolution with the best optical quality, we can drop down a little bit to 250 micrometer. It's still okay, looks good from the optical point of view, but if you have a little bit closer view to this in terms of adhesion of the ceilings for the IGU, and it's a critical point. Yeah? And unfortunately, even if we do this with the lowest resolution, we have not the speed that matches to IGU lines. So that's not a way. Yeah? And to show you a little bit how it works, how slow such a process is, here one example for chromium coated glass that you can good see this process. Unfortunately, it's hard to see. It's in this field here. It's a speed for 10 millimeter width track. The result of this decoating process in terms of optical things as well as adhesion things for the ceilings is really, really good, but it doesn't fit to the time requirements of the IGU. Yeah? You see here the stripe. It's really a good quality, no mechanical issues on the surface itself, no stresses on in the surface itself. It's a good result, but unfortunately, the process is really too low. Yeah. So, solutions and examples. We saw, okay, the bottleneck is the scanning device. And we have to think about it. We are a machine building company. We are not a company to build optical devices itself. So we have to think about it, okay, what's maybe a little bit in the market and think about a little bit out of the box. So we look in other industries and found out a solution at the end to fulfill the requirement to remove coatings, like you can see here, with a white stripe of 100 millimeter in a perfect optical quality. You see it after printing with the black ceramic on it. There are no stripes and there are no stresses inside the glass. And we're looking for an alternative scanning technology. And we found a really old technology. It's a wheel. It's a so-called polygon wheel. What does it mean? The polygon wheel is a device that will be rotated in a really, really high speed, 10,000 rounds per minute. And this wheel has different areas, facets or facets that mirrors the laser beam. And this leads at the end to a line that we can move between the optical tool and the glass itself. And this is the process we have at the end, that the line is running over the workpiece, and this is a big picture from the laboratory state. And last year on the class deck we introduced the first machinery solution, as you can see here, a demonstration tool where we are able to run a stripe of 80 millimeter with 60 millimeter per second speed. You see a lot of material we have here. An important point is to exhaust this material in a careful way to have afterwards a really, really good a result of the optical quality of the removed area. So the effects are, we are able, by usage of this polygon scanning technology, to make a run of maximum 100 millimeter within one step. The area performance is good until 0.5 square meters per minute. The result on the glass itself shows a homogeneous coating removal. We have no glass damages at the surface. And at the end, it's a cold process. This is important too. And the question is how we bring this idea, this laboratory state, in a machinery concept. And this is the task for us as a machine building company. And here you can see the machine concept. We have two conveyors, and in between is a slit, and there's the region where we work with the laser as a tool. We have there on a y-axis the laser tool, and I will show you in a sketch how it works. For the step IGU unit production, we start with a glass that has a mechanical grinding on 3 edges, and the aim is to do the 100 millimeter step. The glass is moving while the laser is working, and so we can remove this step and have at the final end in a very short term, in terms that matches to IGU unit production times, this result what we need. So there are additionally good result because we can do this removal of the coating after the tempering. So the glass is a tempered glass. And this is good for the tempering process itself, even for step units, because the coating is on the glass fully. We have no local bending due to the tempering process, and this leads even to a higher quality of the tempered glass for step units. It's an additional property we got if we use this, and the main point is the cycle time fits to the IGU production. So at the end, I want to summarize a little bit what we have done. A little bit, there was a problem. The process was too slow. The result was pretty good for the product, and we look for alternative scanning technologies and found a very old scanning technology in the market with the rotating wheel, with the polygon wheel. We adapted this to our technology, matched it with the right laser source, and then we got the result that we are able to reach the same time base as we have on IGU units. And this is an important point, and in the last table I give a little bit overview about the laser edge decoding state of the art and the new technology with the polygon wheel. The main thing is that we have the possibility to decode the class in one step with a high speed that matches to other production equipment processes. And so I hope I give you a little bit an introduction how we think if we have a problem, how we solve this problem, and feel free to ask me. We are here we have a booth here at HECLA, and there we have some samples too for this process. And if you are interested in to go a little bit more in detail, feel free to ask me or my colleagues. Thank you.
Thank you very much, Thomas.